Hey everyone, this is Homework 2.7, and today we looked at the average rate of change. And so today we're going to be looking at a couple of examples of that. So the temperature was recorded at several times during the day. We have this graph here showing us that. And since n hours since midnight. So these times represent the number of hours since midnight. For each time interval, decide if the average rate of change is positive, negative, or zero. So from n1, all right, so that would be somewhere around here, likely, or actually here, this is 2.5, so yeah, about there, to n5. So from here to here, we have a negative average rate of change because it's going down. From n5 to n7, so that would be from there to, let's see, this is about 7.5, so 7 would be here. So from n5 to n7, although it goes down a little bit, it does come back up significantly, so this is going to be overall slightly positive, right? Just a little bit. If they were even, then it would be zero, no net change. From n10 to n20, so from here to here. Now notice it goes up and then it goes back down, but that means that our net change is going to be zero. It's not really changing that much. From n15 to n18, so that's from here to 17.5, 18 would be about there. That also looks about equal. I would say that's probably zero or slightly negative. And then from n20 to n24, so from here to here is negative, going down. All right, let's take a look. The graph shows the total distance in feet walked by a person as a function of time in seconds. So this is how many feet they walked for after how many seconds. So distance is a function of time. Was the person walking faster between 20 and 40 or 80 and 100? So 20 and 40 or 80 and 100. Which one is faster? So if we were to draw, this one already has a straight line. If we were to draw a straight line between here and there, which line is steeper? This line is steeper, so between 80 and 100 seconds, they're walking faster. It says, was the person walking faster between 0 and 40 seconds, so from here to here, or between 40 and 100 seconds, between here and here? Interesting. What do we think there? So notice that it does appear that they're walking pretty fast here, but then it kind of levels off. And then here they're walking kind of slowly, but then they speed up. This actually looks like it's following more or less the same slope. So I would say about the same. The average rate would be about the same. And we could actually calculate that, right? Let me erase this just so we can see a little bit better. If we're looking at 0 to 40, right, and then we're looking at 40 to 100, okay, if we were to actually calculate that slope, we could determine a little bit better, right? This is going this way, and then this is going this way. So they're actually about the same. Maybe from 0 to 40 is a little bit faster, but we could definitely calculate that rate of change by looking at they're going approximately 10, we'll say, over 40 seconds. And then from 10 to, or sorry, from 40 rather to 100 here, at the 100, they're a little bit above 20. So let's say 21 over the rate of change. Let's see, so that's 21 minus 10 would be 11 over the rate of the x change would be 100 minus 40, which is 60. So we can see that this one would be a little bit faster because that would be 0.25, and 11 over 60 is going to be a little bit less, all right? So I'd say this is probably a little bit faster. If we just look at the line, it's a little hard to tell, but if we calculate, then we'll see that change more accurately. And again, I got this from the change of x, so 21 over 10, and then, so that's 11 here, and then my change in x is 100 minus 40, which is 60. All right, Jada walks to school. The function d gives her the distance from school in meters, t since she left home. All right, which equation tells us Jada is 600 meters from school after 5 minutes? So it's a function of time. So the input is 5 minutes. The output is how far she goes. And so this would be A. Here, the distance is a function of t, time, the 5 seconds. All right, the height and feet of a squirrel, we got another squirrel running up and down a tree, is a function of time in seconds. Here are statements describing the squirrel's movement during 4 intervals of time. Match each description with a statement about the average rate of change of the function for that interval. So the squirrel runs up the tree very fast. If the squirrel is going up the tree very quickly, then the average rate of change would be large and positive, right? Because they would be going a big distance over a short amount of time. And so that slope would be very steep and therefore very large and positive. The squirrel starts and ends at the same height. The average rate of change is 0. So this means the squirrel's overall still at the same height. The squirrel runs down the tree. The average rate of change is going to be negative. And then the squirrel runs up the tree slowly. The average rate of change is small and positive. So it's still going up, but it's doing it at a slower rate. So our slope would look more like this instead of like this. All right, number 4. The percent of voters between the ages of 18 and 29 that participated in each United States presidential election are shown here in the table. The function p gives the percent of voters between 18 and 29 years old that participated in the election year t. So this is p of t equals that percentage. So determine the average rate of change for p between 1992 and 2000. So between 1992 and 2000, that's our years, so that's our input. That's 8 years. So we're going to divide by 8 because 2000 minus 1992 is 8. And then what we're doing is we're putting our 34.5 minus 42.7. Now notice we can see that from here to here it went down, so we should have a negative rate of change. And we will, in fact, get that when you do 34.5 minus 42.7. We get negative 8.2 over 8. And so if you can leave it like that, or you can rewrite this by dividing negative 1.025 is our average rate of change. So it's decreasing on average by that percent each year. It says pick 2 different values of t so that the function has a negative average rate of change between the 2 values. Determine the average rate of change, and then pick 2 values of t so the function has a positive average rate of change, and then calculate that. All right, so let's look. We already have one example of a negative one. Another negative example is this one right here. In this case, we would do 33.1 minus 42.7 over 1996 minus 1992 is 4 years, and we know that that'll give us a negative. So 33.1 minus 42.7 divided by those 4 years would give us negative 2.4. We're reducing negative 2.4% each year from 1992 to 1996. If we want to find a positive rate of change, an example of a positive rate might be from 1988 to 1992, or you could choose 2000 to 2004, or even 2000 to 2008, because it goes up from 34 to 48.4. So for this, I gave you this one right here, the negative one. For the positive one, pick one of those and calculate it. Remember, you're putting your change of outputs over your change of inputs. All right, so this is the same as your slope formula. Or you can say, oops, oh goodness, there we go, okay. F of A all over B minus A. So you're putting your outputs on top and your inputs on the bottom. All right, Jada walks to school. The function D gives her distance from school in meters as a function of time in minutes since she left home. What does D of 10 equals 0 represent? So this means after 10 minutes, she is somehow 0 meters from school. And so this means that after 10 minutes, she left home and she is now 0 meters from school, which means she is at school. So after 10 minutes, she is, you could also say, at school. All right, that is all for your homework tonight. I'm going to go, your code word is flashlight. Flashlight is your code word. I have a flashlight sitting in front of me, so that's why. I'm going to go back to this classwork real quick just to show you an example from this one. The average rate of change from A to B, B to C, and A to C. So from A to B, we're looking at from here to here. Our starting value, we can probably estimate, is 1 to 1, let's say. Okay, or 0, 1 rather. And so here from, oh, I'm sorry, it says from A to B, not from that point to that point. Let me fix that. Okay. So we're looking from here to here, the slope of this line. And so we're going to use our outputs first. So 9 minus 3 all over 6 minus 3. And we'll get 6 over 3 equals 2. And it's positive, and that makes sense because our line is positive. The little person's going to go climbing up the line. Then we're looking at from B to C. All right, and so in this case, I'm going to start with 11.2 minus this output, which is 9, and then this input, 9, minus this input, which is 6. You'll get 2.2 over 3. You can further calculate that if you'd like. And then our last one is comparing the very beginning, this point, with this point. So I'm going to start with this one. Remember, we're starting with our last point, 11.2 minus, this time 3. And then our inputs, 9 minus 3 here. You'll get 8.2 over 6. And again, it's still positive, still net positive because we're going up here, okay? And so again, you can go ahead and calculate that more exactly. But that's how you're doing this part. So you're going to do the same thing for this one here. All right. Again, code word for today is flashlight. If you have any questions, feel free to text me. Happy homeworking and see you tomorrow.